All right, so one of your assignments today is to wrap up this lab. Up here it says Lab 5.1. We've been working on this. It's actually now been renamed to 5.1b. You did a 5.1, that online simulation. All right, so what you'll find here is we already did. Here's period 4-5's work. We also had period, let's back up a minute. Is that, 4-5. Where's 3-4? There it is. We have period 3-4's work right here. Both of these are already posted. They've been posted on the drive. You click the Unified Materials through the top of your classwork there, the very first topic, Everyday Materials in Classroom, and you'll pop these up, no problem. They walk you through the calculation. The only piece of the calculation that might have given you a little bit of trouble was over here. This was a new equation for us. And so with this new equation, we were looking to get the centripetal force. And so this actually, and focus on what I'm saying right now, because this explanation you're about to get is the answer to question 2 on the back. You're going to do the conclusion questions on the back. In fact, you're going to do them as written. So question 2 on the back is answered by what I'm about to say. So please hang on every word. Okay. When we were looking for the mass, we said we needed the centripetal force. So let's go nice and slow here. The mass is moving in a circle. It is turning. Even if it's not a complete circle, it's turning. Anytime an object is turning, there is a centripetal force. That's it. Just like we knew we needed an XYR chart when we saw a curved trajectory here for circular motion, or even just part of a turn, part of a circle. Anytime you see an object moving in a part or complete circle, there must be a centripetal, a center-seeking force. And so here there is. Now, we just call it FC. Without even knowing what it is, we know turning FC, boom, there's our FC. The next order of business is figuring out, well, not all FCs are the same, meaning there are different reasons that an object experiences an FC. In this case, for example, there is a string pulling on the stopper. When a string pulls on an object or a rope pulls on an object, we give that a new name. We call that tension. So here, the FC is the tension in the string. They are one and the same. It's not just that it causes it, it's that it is exactly it. A lot of it's there. Anyway, so the tension in this string is the centripetal force. But if you follow the string all the way down, the tension in this string is caused by the weight of the hanging mass. So in fact, if you follow the reasoning here, let's put some arrows on this. The weight of this hanging mass, which comes by way of its attraction with the Earth, is the tension in the string, is rotated up here by that little handle, the tension in the string, is the FC. They are all the same thing. So there's question 2 on the back. But anyway, knowing that they are the same thing allows us to calculate FC over here. So knowing that FC is ultimately caused by and theoretically equivalent to the weight of the hanging mass, now we have the ability to calculate what is the weight of the hanging mass. And so many of you did this already, but it's not bad to review because it's coming up with our next set of questions and topics after the break anyway. So if you go over on PRT 6, what you will see is weight, force due to gravity. They are one and the same, and they go by the symbol F sub G. There are a couple equations for them. You're actually going to use both during this lab. But on page 1, so this is lab 5.1b, page 1 at the, the beginning there, page 1, what we were doing there in the bottom, you're going to use this equation. This equation allows us to input the mass, M is mass, input the G. Minuscule g is the acceleration due to gravity or gravitational field strength. We'll see about that in a second. And if you input both of those, what you will output, what you will get out is the Fg, the weight. It's what we want. We already know the mass. We've determined that. We talked about what g was, but let me just remind you. G, little g here, minuscule g, acceleration due to gravity, is what we've been using, boom, right here on the front of your PRT. Acceleration due to gravity, minuscule g, 9.81 meter per second squared. So, knowing those, so we know minuscule g, we know m, cross multiply, you will get the fg, and then that fg can get plugged back in as the fc. You also separately figured out the centripetal acceleration. Not both classes had the same number. So I know this class we have here 98. I believe the other class, we got a different number for it. We might have gotten something like 65 or whatever it was. Go with the numbers, that the magnitudes that come from your class. Same process though. Notice here, yeah, with different colors in the other class, but the same exact process. All right, let's get on to page 2. So on the diagram, if you don't have this paper printed, just draw a circle. Put your stopper over here at the 3 o'clock position, you know, like a clock. 12, 3, 6, 9. So the 3 o'clock position is the stopper. And here it's rotating, you see, with the arrowheads. It's rotating counterclockwise. So you're going to draw the velocity and centripetal force vectors at this position, at the 3 o'clock position. Number 2, we just talked about, handle it. Number 3, you did on the front, handle it. Number 4, go and mass your rubber stopper. Write its value, or its, I don't like that word value, write its magnitude here. Okay, the magnitude of the rubber stopper is approximately 14 grams. So just put 14 grams, and you then have to convert this to kilograms. By the way, this was a mistake that some people made on the quiz. You got a small penalty for it. When you run that FC equation, FC equals mv squared over r, or MAC, that mass comes out in kilograms. So we typically traffic in kilograms. So when you use the scale, which I did, it's actually a balance pretending to be a scale, in the classroom, it said 14 grams on it. You have to convert that to kilograms. And then you're going to compare that to what you got right here in the front. Your equation, by the way, in the front automatically came out in kilograms. I don't think any of you will be dead on 14 grams, but you'll be fairly close. All right, how do they compare? Determine the percent error. Sources of error. You know, we've been getting a little more complex than we typically do, and I like it. So you're welcome to call this, instead of a source of error, a source of uncertainty. That's even better, more accurate. A source of uncertainty here. You know, where is it that our measurements maybe were off? And there are a few obvious ones. I mean, we did a lesson in the beginning talking about the spin rate there, talking about counting 1 versus 10 versus 30 revolutions. There were some comments we put on that. And if you go look, the Google Sheet with the comments is in the Lab 5.1b assignment on Classroom. So pull that thing up. You got some comments in it that'll help you at least with one of these. All right, last part. Time to use your brain. This one is fantastic. And in fact, if you look back at the very heading, the introduction rather, you're an astronomer in the early 1800s, which was an exciting time to be a stargazer, beside the fact that we didn't have the light pollution we have now. All right, fresh off an accurate determination of capital G. What are we talking about? We'll see in a second. You are looking to determine the mass of a planet that you've been watching since childhood. All right, this is not a make-believe thing. This is how it used to go down. Fortunately, the mass of the sun is now known, and the orbital distance of the planet has been determined. So there's a lot of history in here, which if any of you are interested, look up the history of the transit of Venus. Pretty cool history. Anyway, you got to find the planetary mass. So the point of all this here is that in a very real sense, this system you see is very much like a star is here, a planet is out here, the planet is orbiting the star has a certain amount of mass. Now, we have our mass drawn down here, but in fact, the mass of that star would be in the star. But just because of the constraints of the strength of gravity and how we could possibly simulate this, we had to have our mass hanging down here. But really, this is just like having the mass in the star, the planet orbiting. Here is the orbital distance, and there is a force, a centripetal force. acting on the planet. And in fact, this is actually the notes we did in class on Thursday. The centripetal force is not tension in a string, because there is no string connecting the sun with the planet, but there is the force due to gravity. The centripetal force is the force due to gravity. That's the big connection here. So this scenario we have is in a lot of ways similar to trying to figure out the mass of a planet orbiting the sun. And astronomers / physicists have used this calculation to do that. All right, so let's go down over here. This says generate an equation that shows the relationship between speed and orbital distance. Now, unto itself, you might say, wait a minute, I don't really know what you're talking about. But let's check this out. Here's the starting point. Here's the starting point. Going back to that picture from the front. The picture is, here's the sun. Oh, that's fantastic. I'm teaching a class, though. Can you go up and shut the door real quick? Thank you. I got it. Thank you. You threw it. Be gentle with it. Okay. It's nice when they give you imaginary bison. That way they can throw it to you from the steps. All right. So I'm doing a class right now that's being recorded. All right. So here is FG, which is the FC for the planet going in that orbit. Now, how do we make sense of all this? Well, bring this equation down. We want V and R. That should give you an idea, like V and R. Well, V and R are both in the FC equation. So instead of writing FC, we could write the equation for FC, M V squared over R. Now, we need to be very clear about what gibbons we're talking about. In fact, we need to be very clear about our subscripts. This whole equation, mv squared over r, as we delivered it on page 1, mv squared over r, here it is. Here it is. The mass was the moving mass. In this equation, mv squared over r, it was not the hanging mass, it was the moving mass. So the hanging mass is what we use to calculate over here the FG. The moving mass went into mv squared over r. That's the moving mass. And the r, of course, is the distance between the moving mass and the center here. That was that radius. So we need to be real clear. You see why in a moment. That when we're calculating this, this is the moving mass. And in this picture, what is it that's moving? It's a simplified picture, yes. But the thing that's moving is the planet. So this is really the mass of the planet. This is the speed of the planet. And this is the radius at which it orbits. So that's, we can put a little O, the radius of orbit. Okay. On the other side of the equation, we have FG. And this is where we're going to use an equation that you will come to know well. You're going to use the other FG equation. Here it is. I know this is brand new to you, but don't worry. It's just algebra. It's just physical quantities. FG we've been talking about, that's the weight. R. Let's be very clear on the meaning of R. R can mean radius, but R also means distance between centers. So that's that orbital distance. M is just mass, but there's an M1 and an M2. That's not squared or anything like that. M1 and M2 just means mass 1, mass 2. And then big G, universal gravitational constant. When you see the word constant, you go back to PRT 1 and you check out the list of physical constants. Big G is actually right here. Boom, first one. Universal gravitational constant. There it is, that funky number. We'll worry about that more later. Fortunately for you, we're only going to be dealing with letters. So this equation is going to be what we use on Lab 5.1b, page 2, question 7. That's 7a, whatever it is. So let's go over there and do it. So here, instead of writing FG, we're going to write the equation for it, which was big G. M1 and M2 are the two objects. In this case, M1 could be the planet. Doesn't matter which is which. And M2 is then the star or the sun. So that can be the sun. And all this thing is divided by r squared. And that r is the same r as before. That's the radius of the orbit squared. There was the equation. So all we did is we took the FG equation, put it here, FC equation, put it here, and now this is nice because it's got the letters V and R, and that's what we wanted. Now at this point, it's your job. Here is the relationship between V and R, and so here's what I would like you to do. I would like you to solve this equation for V. Solve for V. Which of course means you're going to have something that says V equals, and you're going to have a whole bunch of stuff over here. So there are things that will cancel. There are things that will not cancel. The subscripts matter. Mass of the planet are the same thing. Mass of the planet and mass of the sun are not the same thing. Radius of the orbit are the same thing. So there are things here that will cancel. Solve for V. Next, generate an equation that will show the relationship between orbital time t and orbital distance r. Now this may seem like, wait a minute, now how am I getting this in here? But it's actually not bad at all. You will have found an equation that has V equals, and there's going to be a bunch of stuff over here. The way you would write this in math class is you're basically going to have V as a function of, let's see what will be in there. G, mass, I'm not going to say which mass, R, yeah. V as a function. So basically you're going to have some equation with G, M, and R. Capital G, M, and R. Now, when you have that equation, follow me now. You're going to have that equation right in front of you because you just did it up here. Here's what you're going to do. We can get period, that time for one orbit, into this equation. How? By pulling apart the V. You already know. So watch this, what you're going to do. You're going to leave this alone. Step one, leave the right side of the equation alone. Leave alone. This is only during step one now. Leave this alone. Okay. What you are going to do is turn V into what you know it is. V, use your average speed equation, is of course d over t. We know that. But let's get particular here. We don't want any d and any t. We want the d from one revolution and the time from one revolution, which of course is, you've been doing this, you just had a quiz on it. The distance for one revolution is called the circumference. The time for one revolution is called the period. So you're going to have right here in this spot, circumference divided by period. Now, circumference can be broken down into its own equation. I'm not writing it all for you because you've done this a bunch and you can do it. In fact, you did it on page 1 of this lab. Circumference can be broken down into its own equation. There it is. And the reason you would want to do that is because there's that r. And maybe the r can cancel or combine with somehow the r on this side, or r or r's on this side. So step 2 then will be substitute in your new fraction now for V. This fraction should have something with r in the numerator. I literally just told you what it was. Period in the denominator equals all this other slop that you did in the last problem. Step 3 is solve for t. Solve for period. You're going to have an equation, something like period equals and a bunch of slop. Is it going to be a little messy? Yes. Is it going to be a really cool result? Yes. You may not realize why it's a cool result yet, but you're basically deriving one of Kepler's laws here, which is a pretty cool thing that we'll talk about a bit more when we get back to class. So that's Lab 5.1b. Handle that. the amount of time I spent talking about it will probably far exceed the amount of time you spend doing it. Enjoy, and if you have any questions, let me know.